Okay? If they're in phase, this tells us what the phase difference between those two sources is. If beta is equal to 0, then this is 1, and the intensity that we observe is 4 times the intensity of one source alone. And if beta is pi, then cosine is 0, and the intensity is 0. So now with these two sources, when we go out here and we look at the intensity as a function of angle, we would see if I plot intensity on the radius. Okay, so this, for anybody who just wasn't carefully listening, this is going to really screw them up. The intensity looks like that around the circle. How many oscillations we get all depends upon how far apart the source is, because that term, the beta in there that determines what the angle is to write it all out, it's 2 pi over 2 lambda sine theta d. D sine theta. This is probably the form that
Theta
you see
prime.
in physics too. Right? So that angle that goes into the calculation is pi d over lambda. If d is much greater than lambda, then I'll have a lot of oscillations on my way to sine theta equals 92, sine theta equals 1. First Calvin and then this.
Are those oscillations going to be superimposed over the amplitude of the electric field?
Yes.
Expected to as well?
Yes. So for the orientation that I just chose, the electric field will be constant at a certain radius from an individual dipole oscillator. Because I'm oscillating this way and looking out this way, it's going to be constant as a function of angle. And so this actually is the, let's call it the ideal Young's double slit experiment, where the intensity doesn't depend upon angle at all when they're oscillators this way. Okay, but I could equally well have taken my two oscillators and put them this way, for example, in which case I get no interference around this direction because I haven't changed the relative distance between the two. But when I go this way, around this point here, I will get interference, but the intensity will be high here and low out there. So I'm always modulating the, let's call it the intensity that was supplied by the oscillator to start out with. You can't modulate zero. Okay. Yeah, Josh.
Would that be theta prime?
It is.
Okay.
Thank you. Okay. So that was Young's double slit from, okay, and then the next page that I'm posting in the notes but not talking about here is if I allow the phase difference between the two antennas to, I can make it whatever I like. Actually, just let me mention the consequence there. So what I've just talked about, what we just added here, is when the phase that goes up into the e to the I omega t, there it is, for one of these guys here, we took those two initial phases to be the same. There's no reason that I can't do that and make one of the oscillators out of phase with the other oscillator. I'll just point out that the really nifty thing that you can do there is that that ends up coming in here, right? And not in this angle, but what it does is it shifts the point at which the two waves are in phase with one another. So with two oscillators like this, if with two oscillators I had a maximum here when they're in phase, if I shift the phase a little bit, I can move the maximum this way or that way. So I can steer where the maximum is by by changing the phase between the 2 points. Of course, that's not that useful right here, because when I steer this one over, the next one comes in, right? But in the next example of interference, I better have that example here. Yes. I'm going to touch, yeah, I can do it in 10 minutes, on a neat trick in solid state physics, and a really neat trick if you have a series of ultrasonic sources and you actually want to destroy someone's kidney stones without destroying their kidneys. And that has some personal relevance to me. Okay, so that's a pair. If we put 3 together, we've got a movement. Does anyone get that reference? Okay.
Yes, I got it.
I don't.
I will just say at Alice's restaurant.
Closest thing it reminds me of 1776. I have concluded that one useless man is a disgrace.
I really want to give an entire
to
lecture
a
in
law
metaphor,
firm.
but I don't think I'm capable of doing that.
That would be cool.
Another appears.
All right. So,
The wild woman appears.
what if instead of one antenna,
You have N.
I have a whole bunch of antennas?
Antennas or
Antennae. Okay, I'm going to say that I have n plus 1 antennae, because I need one in the middle. I haven't counted that up. And n over 2 to both sides.
That's exactly right. It's
I
one.
did something right?
It's 1 in the middle and 6 on both sides.
Oh, I did that right, too. Wow. Okay. Now, what I'm about to do in simplification only works when we're far, far away. So I'll do the calculation over here. The total field, all right, is, here's actually the only part where we're far, far away.
in the galaxy far, far away?
That. Okay. E to the minus I omega t minus kr. All right. Times now the sum over all the antennas, n is equal to minus n over 2 to n over 2. I didn't leave myself enough room. E to the minus I n. That's good. Yeah, I'll write it down. KD cosine theta plus delta phi, right? So the n multiplies the delta phi. So each step that I take away from the center changes the initial phase of the array, of the antenna in the array. Yes?
Is this a discrete Fourier transform?
Yes. But no, yes and no.
Okay.
We could do that
Okay.
here, but I'm just going to do the sum.
Okay.
All right? And here's what we can do. Sum n equals minus n over 2 to n over 2 of x to the m is 1 minus x. So this is, I'm just wondering what limits. Does anybody want to tell me? Yes. Does anyone in the class, can anyone in the class tell me what the limits on x have to be in order for this to be true?
X can't be 1.
Yeah. I think 1 is okay.
Yeah. You can
It has to be.
0 over 0?
Here's my problem. The amplitude of that is 1. So I'm going to use that. I don't care what you say.
But then
I'm
you,
going to use it.
then you got 0 over 0.
It doesn't matter. Go, low puzzle. Go.
Right. Oh,
No, because
whatever. I'm using it. Right?
We're good.
Yes, I have a. I've seen this written in Physics 2. In Mastering Physics, we have them write the because. So they have to answer, and then we ask them why. And someone wrote this.
Because you can
Yes. Okay. Not mathematics, but I'm using it.
math works.
Okay, so this looks like
Yeah. I mean, as it tends to 1, yeah.
But it is exactly right.
oh, do I want to write this all out? Yes. But I'm not going to write out the intermediate step. You see that. All right. What I'm going to do is multiply top and bottom by, and I'll write this bit out. So what I would just normally do is just put that directly in there, and I get this to the nth power over this to the 1th power. Okay? And then what I'm going to do is multiply top and bottom in order to turn this into a sine or a cosine function. So it's going to end up looking like this. E to the minus I n. To make life easy for myself, I'll call that beta minus delta phi over 2. Yes. Over e to the minus I beta minus delta phi over 2 times e to the I n beta minus delta phi over 2 minus e to the minus I n beta minus delta phi over 2. Let's call beta minus delta phi over 2. I'll call that x. There we go. So this is equal to e to, oh, I dropped E0 theta over r. E0 theta over r e to the, oops. The traveling wave, right, times e to the minus I n x over e to the minus I x times sine of nx over sine of x. Now we can use L'Hopital's rule. At 0, this is equal to n. And at every multiple, x being a multiple of pi, it's going to be plus or minus n. Let me think about that. Capital N has to be odd because I said that it has one in the middle.
But you said that's capital N plus 1. So do you mean capital N is that entire thing?
No. You're right.
N plus 1 is odd.
N plus 1 is odd.
Therefore, N is even.
For big N, it doesn't make any difference.
So 6.
For
Yeah,
large values.
not 6. It's got to be more than 6.
Large values.
Large values of 6.
I have to be a little bit careful here about the sign, but I think you get the idea. All right. What does that look like? Let's go back up over there. When, oh there, there's beta, right? When beta minus delta phi over 2 is equal to, I have sine functions there, right? Yes. Is equal to 0 pi, so multiples of pi. When that's true, I'm going to get maximum in the functions. In the amplitude. Maximum amplitude. It could be positive or negative, but it's going to be a maximum. And yeah, that's good. And for all the little n's, let me see. Yeah, this is good. So when theta has a particular value, and so I can rewrite this in, this is pi d over lambda sine theta. Right? So I have multiplied by this side, subtract the pi over, and I can figure out what thetas solve that equation. Right? So I find a whole bunch of theta sub n's, for which I have an absolute maximum. Right? And if you think about this, you'll realize that it actually goes through the ratio function, hits a maximum every time this, this is 0. Okay? Every time the sine function, sine of x, is 0. But this function up here is oscillating n times faster. So the function on the top is looking like this, let's say. Sine. Oops. Start there. Is looking like that. That's the function on the top. And the function on the bottom is looking like that. These, I did that wrong. It's looking like that. So the ratio of these two is equal to capital N, because that's what L'Hopital's rule tells us for this function, this ratio here, because that's sine x, that's sine nx. At this point, everywhere else this is finite, so actually what happens is that the amplitude decreases. I get to here, and at this point, it's going to be less than 1, and so on. Right? So what happens is that I get an intensity pattern, which I've printed in the notes, but I didn't bring my computer along to show you. That looks like this. As a function of angle. And equally to the other sides.
That's the absorption of chlorophyll in the visible.
Not even close.
It is.
No, that's in the infrared.
No, the left side is blue and the right side is red.
Well, I'm going to continue that. That will mess you up.
Yeah, no, that's messed up.
I don't know that I've made the right number of oscillations there. Okay. But this is going to be a repeating pattern as a function of angle. Turns out that the number of maxima between here and here, of minimaxes, is n, the number of oscillators in the system. Right? The height is n. Actually, I screwed up here. Sorry. I've just drawn the intensity pattern. I've been talking about here. So just let me rewrite this thing here. It's, let's call it I0 of theta, whatever was coming out of the sources, right? Times some sort of phase thing here. Okay. Times sine of nx over sine of x. The intensity, whoops, it's going to get rid of the phasey thing because I get the intensity, I multiply it by its complex conjugate. Since I'm working with complex numbers, I multiply by complex conjugate. And that gets rid of the phasey thing because the amplitude of the phasey thing is 1. All right? So this leads to an intensity, which is I0, which could depend upon theta, sine squared nx over sine squared x. That's the intensity pattern for a whole bunch of oscillators. And that looks like this. And there are n maxima in that intensity pattern. And the maximum intensity is n squared. So when I have an array like this, now I'll go out there and talk about what the intensity looks like. So I'm out here, and I'm looking at the intensity along some radius, assuming that the array is small compared to the distance away. Right? And now the intensity is really bright in the middle, and then it's really bright out over here, and there are some little lobes in here. But it's really bright right there.